All right. Hi. My name is Jesse Nusbaumer. I'm a software engineer in the atmosphere model and predictability group, which is the same as the SEAL, basically the folks who do CAM, and then a future version of CAM called SEMA. And yeah, we're going to talk about, you spent the past few days running a model. So now what do you, instead of just looking at a bunch of files, we want to actually look at the data, right? Like how is our climate model doing? How do I evaluate it? So quick outline, we're going to talk about, what the output actually is. We're also going to talk about some public experiments that NCAR provides for the community. Here. We're going to talk about the file format, which is NetCDF. We're going to talk about how you can work with NetCDF and different command line tools you can use to operate on them. We're talking about how to view them real quickly. We're then going to talk about two programming languages we use for model diagnostics and analysis, kind of at a strange time right now. NCAR for a long time focused on NCL, which was a kind of language developed in-house, but due to various reasons, we've been moving on to Python. So we're kind of in this transition period. We're going to focus on this one on NCL, but there will be at least one Python exercise if that's more your jam. And then, finally, we're going to talk about the practical itself. So yeah, right. So you ran a model, hopefully, and you archived it. And so you're probably already familiar from yesterday's practical, right? But in your Scratch directory, you should have two subdirectories. One is just the name of your case, right? b.day21. That has two directories underneath it. One is build, which is actually where the model binaries live, and the build logs, which you'll probably never look at unless your build fails. And then the run directory, which is when the model is actually running, that's where all the data is written to. You also then probably have an archive and then the case directory. And that's if you ran the archive script, is where all your data is stored now the model's finished. And again, if you spent time looking at it yesterday, you'll see that there were various component subdirectories, which is where all of the model data for that component is, right? So ATM has the atmosphere, ocean has ocean. There's two others that are usually useful: logs, which is where the run logs are, which are just these very big text files that kind of just give you a bunch of information about what the model was doing while it was running. And then rest, which is where your restart files are saved. So you can always go there, grab restart files if you need to do a branch or hybrid off of a simulation. Now this, I should note that, by default, it goes to this Scratch archive, but you can always change it in future simulations. You just have to modify it. dout. You will see that mouse? Yes. dout s root variable in mrun. So set it wherever you want. Maybe don't do it to your home. You probably crash it, but anywhere else is fine. Also, maybe some of you have some kind of old-timey professors or advisors who may talk about long-term archiving. We no longer do that. And basically the reason is money. It was really expensive to do long-term archiving, and then we ran out of money. So, so file conventions. So everything is output in NetCDF format, and if you want to find your history files and they've been archived, you go again to just kind of your Scratch archive case and then a component, let's say atmosphere, ocean, whatever, and then there you should see files that look like case name.cam, which is the model component, and then an H0 or H. That H term basically says what data is stored in that file. And by default, the model will always output .h or .h0, which is monthly averages. So the model will always output monthly average data. But when you do your own simulations, you can always modify it to output instantaneous data or data that's on different times, right? Like so daily data or 6-hourly data or whatever time period you want, even down to the time step itself. If you do that, then it'll be written in different separate files that'll then be labeled H1, H2, H3. But I believe in this case, you all just have H0 or H files. The other thing that's important to note is that by default, the model writes where we call them model history, but they're really what's known as time slice files, which means that essentially you have a bunch of variables for a single time. And so, for example, and again, this would say something like, I should change this, it's just say b.day2 something. But you have a single month, November of 1993, but it has over 200 variables in it. So, and that's going to be the same for all the model components. One time, but a lot of variables. However, a lot of times when models have been post-processed and then provided publicly, they're in time series format, which means that it's one variable, but it's across all time, a series of time. So in this case, it would look something like this bottom thing. Again, it'd be the case, the model component, and then H0, which indicates a monthly average, but then it will give you the variable name, which in this case is sea level pressure. And this is now over, January 1990 to December of 1999. So a large time period. Oops, did I go? There we go. Finally, if some of you are using CMIP data or any of the MIPs, we also provide them, but they're also slightly different naming conventions than what CESM outputs, either directly or after it's been processed. And that's just because CMIP has really stringent requirements on what all the metadata and file naming has to be. But essentially, it's the same idea. CMIP files are always time series, so one variable over a time period. And they'll have a name convention, something like this, right? So ZG is the variable name, it's monthly averages, it's from CESM2, it's historical. This is all kind of just information on the run, and then it's from the year 1850 to 2014. And the only warning from that is if you're used to using CMIP, don't assume that the CMIP files match CESM, and then vice versa. If you're used to using CESM, don't always assume that CMIP will match. Also, a real quick warning: all these NetCDF files will have a time variable in them. However, the time variable is actually designed to be the last time of the averaging period. So in this case, right, this is a file for December of 2017, but if you were to actually look at time in the variable, it would say, oh, it's January 1st of 2018. That's just because that's the last day that the model had before it output this file. In reality, all of the variables are for December of 2017. And if you're never quite sure what time this file is covering, there's also all of these, all the CSM model files will have time bounds as well. And the time bounds, which will be, literally time bounds, will tell you the actual date range, right? So remember, it's December, according to the file name, it's December of 2017, and the time bounds show, yeah, we started in December 1st of 2017, and we ended at January 1st of 2018. So just as a general rule, if you're just, kind of getting used to these files, don't use time, use either the file name, which should always have the date, or time bounds if you aren't sure. And if you're just curious, the reason it was done is in theory, it allows you to put monthly averages and instantaneous values in the same file. And it doesn't impact CMIP because CMIP has a different convention. Okay, so what is with all these long names, and how should I read all of these files when I see them? So in general, by default, the first letter in your file name is the comp set. So write B comp set or an F comp set. Then you should have E something. So, and that's the code base. So E21 is CSM21. E1 would be CSM1. You might see there is CSM22 that's available, although it's only functionally released. So you might see E22. And if you're looking at pretty old files, you might see C40, but essentially just tells you what the model version was used. Then you have the comp set short name. So like B1850, it's a pre-industrial control for 1850, or F AMIP. That means it's an AMIP run. So prescribed SSTs and prescribed sea ice, and CN means carbon and nitrogen cycles are enabled. Then you have the resolution short name. Both of these are 1 degree. The reason this has a G16 is because it needs to tell you the atmosphere and the ocean grid, whereas an AMIP is only atmosphere and land, so it's only 1 grid. Finally, a description string. Again, this is saying, oh, this is a pre-industrial control for CMIP 6. This is, excuse me, an AMIP run with RCP 85 forcings and SST-ER SST data set. Then finally, just a number, which is pretty much just telling you how many times have you done the same simulation over and over again. And then a letter if you're, for kicks, if you want it. Now, so all of the comp set letters, probably already told us, all the comp set letters mean something, right? So letter B comp set means it's a fully coupled run. F comp set means it's an atmosphere land. I means it's land only, so the atmosphere is just prescribed data. And then G is ocean and sea ice only. So it's prescribed atmosphere and river runoff and the models. The other one, there's a lot of other ones which you'll probably never use except for possibly Q, which is aquaplanet. So it can be ocean and atmosphere where there's no land. Now you may be asking, like, why is coupled start with a B? Why does atmosphere start with an F? And why does land start with an I? And the answer is because back in like 1945, give or minus a few years, someone decided that and it's never changed. So I have no idea why that's the case. And no one seems to know. So one of the things that we recognize is that there's some simulations that are just really hard for any individual to do. That either could be because they need to cover a huge range of parameters or simulations like CMIP itself. It could be because they're large ensembles. It just takes a ton of ensemble members. Or it could be because the model is really high resolution. In those cases, NCAR has tried to run these simulations and provide the data publicly for people to analyze. So if you're interested in, if you're just kind of like, I need a certain CMIP data, or I need a certain, like, I'm using a large ensemble, whatever, I just want that data, you can go to this website and you'll land on a page like this, and it'll split up by model version. So obviously we're CESM2 now, so we'll be focusing on that. So if you were to click on like that link, that CESM2 Experiments, you'd wind up on this page, which lists all of the scientifically validated, publicly available model simulations that NCAR provides. Oops, oh no, that's not good. Did I actually go to it? I did. Okay. Well, I can show you. Oh, well, heck, I'll just show you here. So if you're, you land on here and you're like, you can see most of them are CMIP. A lot of them are some sort of MIP. PMIP is paleoclimate MIP. So I was like, oh, I'm kind of interested in that. You can click on it, actually this plus, and you would see that you provided, first it provides a description, right? So this is an idealized deforestation experiment with certain boundary conditions. It then provides information on where you can get the data. You can use something called the Earth System Grid Federation, which is kind of the infrastructure that all of CMIP uses. Or you can grab it from other locations, like we have a subversion repository. And then finally, let's see if I can do this elegantly. Yes, they all will come with their own diagnostics. So, which is what we'll all be running today in the practical. But essentially, you can click on one of these. See if I can do it, because I'm already out here. So you can click on it and you would see a website like this, which is what the diagnostic produces. And so you'll generate this website yourself. And you can just click on a certain plot type. Like, let's say I'm interested in contours. And then you can click on, and so what it is, the variable, the model variable. So this is like sea surface temperature. This is, in this case, comparing observations. So this is the Hadley Center SSTs. And I can say, like, how does it compare for the DJF average? And there you go. So I have the model at top, the observations in the middle, and then the difference between the model and the observations at the bottom. So you can tell that, like, my Southern Ocean looks kind of cold. So for this particular run, great observations. Okay, let's see if can I go back now? Go. Yes, okay. So that's what I already covered. I mentioned this, the ESGF, but if that's, that can be kind of difficult to use sometimes. And if you want to just NCAR specific data, you can also go to our climate data gateway, which is again, just that, that URL, which I'm not going to click because I already did that once. And essentially, if you go to this website, you will have to register, which is just kind of like a name, like you got to make up a password and stuff. And then you'll have access to all of these publicly available runs that NCAR does with the various, and you can get it by a specific model because it'll all be time series, or not model, variable. And then just, some other, obviously we have all the MIPS, and but along with that, we have very long pre-industrial simulations. So they're very much in equilibrium, right? We have a CAM6 one that's been running for 2,000 years. We have a Wacom 6, which is a high top version of CAM running for 500 years. We also have large ensembles. So, the biggest one has now well over 100 members. Go back, there we go. Well over 100 members. And then we have various different forcing scenarios for those ensembles. Okay, so now you have a model, you ran it, and now you're like, okay, I compared it to observations, but which observational data set should I use? Or, is my model actually perfect and the observations are the problem? If you aren't sure, we try to help with that with this website called the Climate Data Guide. So the Climate Data Guide is where you can go and you can learn about over 150 different observational data sets, including reanalysis. And the one advantage about that is not only do we just generally describe what these data sets are, but we've contacted over 4 dozen people who are experts on that observational data set or reanalysis to describe what are the pros and cons of that data set. So, for example, if you want to compare against reanalysis, it'll say like, oh, MERA 2 is really good about water cycle stuff, but maybe isn't the best if you're concerned about the atmospheric circulation, where ERA 5 might be better for that, or vice versa. And also even provides direct comparisons between observational data sets of the same variable, right? So for example, there's multiple different SST observational data sets. So on this page, you can go and you can see like, oh, okay, here's 6 different observational data sets of SST. How do they vary from each other? What's their resolution compare? Things like that. So now let's actually get a little bit into the nitty gritty. So, right, you have NetCDF file. So what is a NetCDF file? NetCDF stands for Network Common Data Form. The biggest pro about it is it's a file type that contains its own metadata. So, and we'll go through about how to extract that, but that means you're not just getting like temperature, you also can know what are the units of my temperature, what kind of temperature, is it 2-meter temperature or skin temperature or whatever. And that, along with that, makes it very portable. So you can just move the .nc file around and it'll carry all of that with it. The other advantage is, at this point, NetCDF in the modeling community, I would say, is probably by far the most common file type. So that means many programming languages have abilities to access it. And so that includes compiled languages like Fortran and C, and then also kind of more, the more typical analysis language, right? MATLAB, NCL, IDL. I don't know if anyone uses IDL much anymore. And then, and Python. The disadvantage for the different versions of NetCDF, and some older versions did have some problems, particularly with compression. So you can't, a lot of times you want to compress all these NetCDF files so they can take up a huge amount of space. But with older versions, pre-NetCDF 4, that could be difficult. The other annoyance is that if you're using some languages, you have to be really verbose in how you're, you have to write many, many lines of code to open a NetCDF file and get the variables out. That's not true for NCL, and that's also not true for modern packages in Python. You can just say, this isn't real syntax, but you can just say, get me this variable, and it'll get you that variable with the metadata. And if you want to know more about NetCDF, there's some links for you to read up on it. So anytime, any place that has NetCDF is also going to have NCDump. And NCDump is arguably the most important command for working with NetCDF, because it's the one command that allows you to actually open the file. If you're going to go and try to use a text editor and open a .nc file, it'll just get a bunch of hot garbage because it's all a binary file, and so text editor doesn't know how to open that. So if you want readable numbers, you have to use NCDump. The most common use of NCDump is this -H, which you see right here. And basically that says, give me all the metadata, but don't output the actual numbers. And so for this, and so the thing on the right is what that would look like. And so to step through it, almost every NetCDF file is going to have a dimension section, which is kind of airing. These are all the possible dimensions that every variable in this file could have. And they have names, right? So lon, lat, and time. You also might notice time has that unlimited in capitals. That means it's what's known as a record dimension. We'll talk about in a bit when we get to the NCDF operators. Then you have the variables. And you notice almost every NetCDF file is going to have variables that are only dimensioned one dimension and have kind of a similar name. And those are what's known as the coordinate variables. And so that's just saying, basically what it does is the dimension up here just says there's some dimension that's 73 numbers long or elements long. Whereas the coordinate variable tells you what are those actual numbers and says, okay, well, it's latitude and it's degrees north, and it would give you some number range, right, from -90 to 90. or 90 to negative 90. And so, yeah, again, latitude, you do it for every dimension, longitude, time, and these things here, these kind of metadata are often in NetCDF speak are called attributes. So they're attributes of that variable. And really common ones are units and long name. Finally, you would have the actual variables that you probably care about. In this case, there's only one, sea level pressure. But again, it's dimensioned time, lat, and lon. So which makes sense, right? It's surface pressure and all latitudes and longitudes for various length of time. And it gives you, again, same thing, long name, units. Another really important thing in NetCDF world is missing value or fill value, which is kind of what its name suggests, right? It tells to any program that's using this NetCDF file, hey, do you see a grid point that has this ridiculous number in it? That means that it's not a real value. It's for whatever reason, it's missing, or I had to fill it, or it's just wrong. So just ignore it. So it helps a lot for things like plotting, because that way when you plot, instead of just getting this huge red spike right there for that plus 36, it just masks it. And then finally, you can have global attributes, which is kind of metadata for the whole file. And usually what this is like, where did this file come from? In this case, it's from NCEP reanalysis. And then did anyone operate on it? We'll learn about the NetCDF operators. When you do that, that'll add information to this global attribute saying, hey, someone like concatenated this from two smaller files or something like that. Now you can use NCDump to actually look at the actual variable itself. It'll print out onto the screen the numbers. So if you did NCDump minus V of SLP, it'll print out the sea level pressure. Should be careful about this though, right? Because it's dimension time lat lon. So there will be 744 times 73 times 144 numbers that are going to be printed to your screen. It's kind of a lot. So generally we recommend piping that, which is what this little letter thing is. You can either pipe it to something like less, which you can look at it all, or you can just have it output directly into a file, like a text file, and then you can look at it more closely. And then finally, I mentioned types of NetCDF, right? There's older and newer versions. You can use NCDump minus K to figure out what version you are. So in this case, NetCDF 4. Then finally, time. If you notice, time is in units of hours since some date. A lot of times that can be hard to read. So you can use this minus T to output dates and times that are more human legible. Okay, so you have NetCDF files. A lot of times you want to do things to them. And one of the best way to do things to them is with the NetCDF operators, which are command line functions you can use to, to do things. Here's what I just said. One of the big advantages with these is you can use what are known as wildcards. So let's say you had 20 files in a directory and you wanted to average them all. You won't have to go through and type every single file. You can just say like, file star.nc and it'll grab all of those files. There's a ton of NetCDF operators out there. I recommend going to their webpage if you want to look at more. We're just going to go through kind of some of the more common ones that are more frequently used, at least at NCAR. So one of the common ones is the NetCDF record averager. So remember when I said time is a special record dimension? So what that means is that certain NetCDF operators like this one will know, okay, this is the dimension on which I should average. So if I were to use NCRA of two different files that had time as the record dimension, so let's say this is January and February, NCRA this would then be the January-February average. So this file wouldn't have time, but it would just be lat lon and the average of those two. Similarly, instead of averaging, you can concatenate, which just means attaching two things together. So this is saying, okay, give me January and February and attach via time. So now this new file will have January and February. And so this is personally, I find this a really useful tool if you do have a bunch of these history files and you need to make time series, right? Because you can just attach a bunch of them together. Oftentimes you have an ensemble or like, let's say multiple model runs, which kind of cover the same grid and they cover the same time, but you still want to know what the ensemble average is. That's what NCES can do. So again, to say these are all January of these 3 different model runs, I can do NCES and I'll get an ensemble average for January for that run. And it used to be just averaging. I think it's now NCES because it can do other statistics. I think you can get like standard deviation and things as well. NCDiff is difference then. So if I have two files, as long as they're the same grid, I can do NCDiff and it'll just tell me what the difference is. So I have two simulations. I just want to know what's the difference in, temperature. This will probably, this is really useful for debugging. So, if you have one model that's going off the rails, it's an easy way to see that. Then there's NCKS, which is everything they couldn't figure out have its own own NCO operator. So it literally stands for kitchen sink because it's everything in the kitchen sink. And it can do a ton of stuff. I'd recommend looking at the documentation if you're interested. But what's frequently done is it's used to pull out variables from these time slice files. So, right, for example, I have an ocean, I have a pop file here that has a bunch of different variables on it, just one temperature. So I can use NCKS to pull out just temperature. Of course, I can do that for multiple. You can just make a list of variables. The reason this might matter, in this pop case, so NCKS will pull out the coordinate variables that temperature depends on. But for example, in the pop files, there's actually different grids with different lat and lon. And so you may want to extract them directly because they won't be extracted automatically. I should also point out that one disadvantage to NCKS, it doesn't allow wildcards. So I can't hit, give me -v temp and then start at NC. It won't work. Other ones, NC attribute editor. That means, those attributes like units and long, if I just want to change that, this does that really quickly. NC rename, I'll let you figure out what that one does on your own, but you can probably guess. And then NC Flint, which allows you to interpolate between two files, and I don't know how to pronounce this one. NC PTQ, which basically allows you to pack data, which is kind of like compression. But again, be wary that it can have trouble with older versions of NetCDF files, like NetCDF 3. And then some general kind of flags. So -v for any of these operations will operate only on the variables listed. So again, NCKS says pull out TU and surface pressure. If you do -x -v, then it does the opposite. Pull everything except the variables I list. So in this case, give me everything except chi and cloud tote. -d is operate over a subset. So a lot of times it's a spatial subset. In this case, and it's a little hidden here, but it says for lon, notice these two numbers have decimals. So that's saying give me 0 degrees to 180 degrees in longitude. But then for latitude, since they're just integers, it's saying, and then give me the latitudes from element 0 to element 63, which is not necessarily what the latitude values are. It's just the values for those elements. And then -h allows you to, remember I said the NetCDF operator will oftentimes write a global attribute to the new file saying like, NCKS did this. That can be really long. And so sometimes -h is a way you can modify that yourself and not have it write a huge long attribute. And then, there's many other options. And then I think we're a little behind time. I'll just say quickly, any of these operators you can use inside of scripts. Either that's like a shell script, you can use it inside NCL, you can use it inside Python, you can use it inside basically any language that can talk to the shell. So that's really advantageous because, to be honest, NCO are very heavily optimized, so they tend to be much faster than if you were to just write concatenate on your own. So I would generally recommend doing that if it fits. Then also to go quick, there's another thing called the climate data operators, which kind of do more specific climate analysis things, EOF, detrending, etc. If you want to look at that, there's the link to do so, but I don't cover it too much here. Finally, another really useful tool that I want to cover quickly is NCView, because even though I said NCDump is to look at it, it really just prints out numbers. A lot of times you want to literally look at it, right? You want a picture. And so NCView is probably the easiest tool to do that quickly. You literally just have to type NCView and then the dot, whatever file you want to look at. And you can actually put those in order. You can have multiple files here, and it'll, as long as they have a record dimension, it'll attach them as the record dimension. And what you do is if you click that, you would get a pop-up window that looks like this. That allows you to select the variable you want. and then allows you to move back and forward through the record dimension, which is usually time. And you would then get a picture. So in this case, they selected surface temperature, and so you would get a map of surface temperature. So that's a great way to see, is your model doing something sane or not? Panoply is another kind of equivalent to NCView. It's a little more powerful than NCView, but it also takes more effort to kind of install and use sometimes because it involves Java. But I'd also recommend checking that out if you're interested. And there's the link. Okay, so remember I told you there's two kind of programming languages we're going to be using in the practical. One is NCL, the NCAR command language. That was the one that was developed in-house for long decades, I think. Given that it's literally specialized to work for climate science and atmospheric science and geoscience. So that means it's really easy input-output, particularly for NetCDF files. It has a whole bunch of graphics features, particularly for different kinds of map projections. And it has lots of built-in functions, specifically for geosciences. So again, things like UF analysis or spectral analysis or trending, et cetera. There's already functions that exist. And the other real advantage of NCL is their website, which you see links there. They have 1,000+ examples. So if you kind of are like, I want to do something and I have an NCL script, it's great to try to look on the website and can likely find an example that's at least similar to what you're doing. There is one disadvantage to NCL though, and that's it's basically no longer being actively developed at NCAR, and NCAR was the only place that was doing the development. So that means NCAR is still trying to support it and keep it alive, but they're not advancing it. Instead, they've moved on to Python. If you aren't familiar with Python, it's an open source scripting language, and it's very general purpose. So actually, there's a huge amount of applications to it well beyond geoscience. And there's approximately 1 gazillion tutorials online. So if you just type Python, you just type the word Python, you're probably more likely to get the language than like the snake. So it's very widely spread. NCAR and other groups are actively working on packages in Python. Python tends to be a packaged language. So it's specifically designed for geosciences. So if you either never use Python and want to learn, or you know Python, but you're not sure what packages are useful for geoscience, I would strongly recommend going to this Project Pythia page. This is being developed by NCAR and others to literally be a center for training and documentation and examples. So if you've never written a line of Python, or if you have, but you're like, I don't know how some of these X-array works or Dask or these different packages you may have heard of, this is a place I would strongly recommend going. The other NCAR developed Python package I want to emphasize is Geocat. And basically Geocat is being designed to be the Python replacement for NCL. And so literally the goal is all of those NCL functions and mapping projections, et cetera, that exist in NCL now will, in theory at least, be eventually added to Geocat. And just like NCL as well, they're trying to build up an examples page where you can see like, oh, how do I make a Mercator map, or how do I do a polar map, or do regridding or whatever. And so that's what these links are for. And then finally, I just want to give, because it's run by UCAR through Unidata, but if any of you do meteorology or like weather forecasting related projects, then MetPy is another good resource to look at. Finally, in just terms of the coverage, before we get to the diagnostic packages themselves, NCAR also has something called Jupyter Hub, which I know at least one of you is familiar with. And essentially, right, as you've done this whole tutorial, what you've done is you've opened a terminal, you've typed SSH blankety bloop, and then you get into the supercomputer. So with Jupyter Hub, it allows you to get into the supercomputer through a browser. So what you would do is you'd open a web browser, you'd type in that URL, and then you'd have to add in your login credentials, but then you would get this page or something that looks like this page. And so there you can open terminals, which are what the consoles are, with specific computing environments. So if you wanted to use MATLAB or Julia or Python or Bash, or you can open something called notebooks. And we're not going to talk about notebooks today, but essentially it's these files that have a collection of cells that have code you can run, but then also kind of metadata markdown stuff that describes the code. In the future, a lot of this tutorial will likely be using Jupyter Hub. So you're kind of you might be the last generation who are, true SSH champions. So, okay, let's talk about the practical. Let's talk about the practical now that we're getting there. So you're going to be provided with a bunch of scripts. Mostly there's going to be NCL scripts to post-process the data that you've all generated from your model simulations. What do we mean by post-processing is basically we're converting from, remember that time slice format, like a bunch of variables with 1 month, into time series. So one variable per file, but a lot of time. We're also doing a little bit of interpolating and regridding. In particular, CAM is on this weird hybrid sigma pressure coordinate. And so what we do is we interpolate that to just strict pressure levels. They all use NCL except for one, which is optional, which is the ADF, which is a new diagnostic package, which is Python only, which you also use run. And again, I kind of showed this already from that web page, but essentially what they are is these are all scripts that just generate, do the post-process, and then generate a bunch of plots like this, right? So contour maps and polar projections and seasonal cycles and Taylor diagrams and time series. They also, what's really helpful for a lot of times, they produce tables. So they produce kind of like mean, max, averages for variables, and then what's the average difference, and trends, which can be helpful for knowing, in Cecil's last talk, what you ultimately want is you want the top of atmosphere radiation to be 0 for a balanced run. And so we use these diagnostics to tell us what is the top of atmosphere radiation. So how many packages will there for this practical? Well, there'll be 4 NCL-based ones, one for the atmosphere, sea ice, land, and ocean. There'll be one Python-based one you can run that's atmosphere and climate specific, which is ADF. And there finally will be 2 other packages, one other package, I'll say, because they're similar to CBDP, which is not component specific. Instead, it's focusing on general climate modes of variability. And the reason we use this is because this is generally the quickest and fastest way to generate general plots for your model to ask, how does my climate look, right? What does the atmosphere look? What does the ocean look like? What does the land surface look like? Now that I've simulated it. And it's a great way, again, to see is something going off the rails, or is there a big bias, right? Did I tune something and now all my trees are dead? So that's where these really help out. And just a FYI, they're useful, but at some point you will likely have to write your own code, right? Because you probably all have a very specific research topic that only you know how to plot. And so we can't help you there. I already showed you all this. So this is what it would look like. Okay, so most of them, again, will show climatological averages for a particular part of the atmosphere, part of the Earth system. However, the CVDP, the climate variability diagnostic package, is a little different because it shows it's not component specific. Instead, it's kind of mode specific. So it can provide all sorts of different diagnostics on anything that ends with an O, right? Like the PDO, the ENSO, the NAO, the AO, the AAO. It used to be the AMO. Anything. It also provides, again, things like time series, and trends, etc. It also provides, it's part of what's known as ESM val tool, if you're used to that. And so what that does, it also then allows you to do the CVDP on a bunch of different kind of simulations at once, or different ensemble members at once. So for example, you can get a panel plot like this, and this is actually for CMIP models, but you can then say, okay, how does the PDO compare amongst a bunch of different models? Yeah, so here's a similar thing, but this is again for El Nino. And so just showing it's not all map projections, you can get these sort of, this is Hofmuller diagram, maybe. And then, sorry, you can do trends as well. So again, right, we might concern yourself with global warming. So this is a way to see if your model is doing that. And remember, we have publicly available model simulations. So we also provide publicly available applications of the CVDP to some of these large ensembles and CMIP sort of stuff. So again, if you're kind of interested in like, oh, how is ENSO doing in these big CMIP runs or large ensembles, you can go to this website, which is run by the Climate Variability and Change Group, and you can kind of get that information without having to run through it yourself. Finally, there's one last diagnostics package with Python only, and that's the AMWG Diagnostics Framework. This one is, right now, it's only can do 2 things. It can run atmosphere diagnostics, so it can give you the climatological averages compared to either model or OBS. and it can also run the CVDP. So if you're interested, basically, if you're interested in doing something Python-y, then I would recommend the ADF. However, it's in development now, so it doesn't have as many plots as the standard NCL one. It's still trying to get to that stage. If you are interested in it, you can go to the GitHub, because that's where basically all of it's hosted now. Again, I want to point out all the diagnostic packages either compare against observations or against another model. So if you have a baseline model, you can compare against that. Otherwise, OBS. One thing to note is all of these packages are designed for decades of data. We also only have a few years. They'll still run, but you might see that some of the plots look a little weird, or maybe something's missing, or the stats aren't right, and that's just because there's just not enough model data for that to do the analysis. You can take all these packages home with you. The ADF is designed to be easy to port, and I can help with that. The other ones can also be ported. They're all on GitHub, but they have some extra requirements. Particularly, they may require having those NetCDF operators, having NCL, and then a Linux package, Unix package called ImageMagick. We are working on putting all that into as a container, however, so hopefully in the future it'll be much easier to port all of these diagnostics packages to wherever you want. And then finally, while you're doing the practical, the last step of all these packages will basically be Firefox index.html, which allows you to open the website and look at your plots. If all of us did Firefox.index.html all at once, we would kill each other. So it would, not literally. So I mean, like, it would be very slow. So if you run into that situation where you've hit Firefox and it's just really slow and grindy, then just let one of us know and we'll come and basically we'll help you tar it up, bring it to your laptop. And then it'll be much faster to open by any browser, whatever browser you have on your computer. I also want to point out that for whatever reason, maybe all of the packages do require some time. They require usually over a year. And there might be some reason why yesterday your simulation just didn't run, right? Like maybe it failed, or it's just all nans or whatever. In that case, we provided well, actually, Adam Phillips, who will be helping us today, has provided an example of yesterday's run with all 38 months. So if your run doesn't work for whatever reason, feel free to grab Adam's, and you can use that one. Just a couple of warnings: if your model run is a few months into a year, don't use that year. All the diagnostics packages require complete years. So if you have 3 years plus 2 months, only use the first 3 years. Also, you'll have to enter times into some of these. Don't add the zeros. You can with the ADF. The ADF doesn't care, but for the other ones, don't. If you have 003, just add 3. Don't add 003. And then just like the model run, they'll all output log files. So if something fails, we can always look at the logs and see what went wrong. So there's a bunch of. We're now going to quickly. What am I doing on time? You all. Okay, well, we're a little fast. I'm going to go quickly over this, but this is now where the practical starts. One thing I want to emphasize: you are not expected to run every single diagnostics package. I'm sure you all have a particular favorite component, so just feel free to run that component's diagnostics package. And then if you want to run other packages, feel free. I'm not saying you shouldn't run it all, but just don't feel like you have to. So real quick, what we're going to do is do it through a couple of basic steps that everyone has to do. And I'm going to put the slide back up and leave it. But essentially, you then want to go to these specific slides for the particular component you're interested in. And note as well, that includes the CVDP below, if you want to just run that, or the ADF, which can be the ADF standalone or the ADF plus the CVDP. So real quick, and we'll start this in 2 minutes, but basically we're going to SSH into Cheyenne. And then if you're doing the ADF or CVDP, you'll skip ahead. Otherwise, you're going to want to copy, just like you did yesterday and the day before, you're going to want to copy an environment file. So .profile, or if you're one of those crazy CSH people, you can do TCSHRC. And you want to source that. Then you're going to make a scripts directory, and you're going to copy again Adam Phillips's scripts, which kind of contain all these diagnostics in an already kind of set up fashion, into that directory. And then you'll go through all of these steps where you're essentially you're setting up your environment, you're making some directories, you're setting up the diagnostics components, and note that you need double dashes for these, and then providing basic information like where's my model data and what's the grid. And after that, you can run all the NCL packages. I'll skip ahead real quick. If you do the CVDP, excuse me, it has slightly different direction. So you start here, and then you're going to actually go from Cheyenne onto Casper, which is our data analysis machine. And then you're going to have to do some editing of something called the name list. So just, it says gedit here. Obviously, you can use whatever text editor you want. And then it describes here how to do it. And then finally, if you do the ADF, you're also going to do the same thing. You're going to log on to Casper. And then you're going to set up your environment using Conda, which, if you're not familiar with, is essentially another command line thing. And then clone it and then do the same thing. You're going to open a file, change a few things, and then run it. And then finally, if you're done with everything, there's some other exercise and challenges. Yeah, feel free to do. Okay, so sorry, that might have been really quick. Is there any questions before we just get going about anything? All right, take that as I nailed it. So, all right. But yeah, I'll be around. Adam Phillips will be around. Other helpers are around. So just like the last periodical. So thank you all for listening. And yeah, good luck. Hope it doesn't die. Break anything. Thanks.